Hello, I'm Jacob Hurst, and today I'm going to be presenting on my Storm Peak Labs data analysis project that I've been working under my supervisor, Naruki Hiranuma. All right, so let me go ahead and go to the next slide here. So a little background on our sample locations. So our samples were taken from Storm Peak Laboratory, which is at 40.455 degrees north, negative 106.744 degrees west, at a height of 3,220 meters. Okay, Storm Peak Labs is placed strategically on top of a mountain barrier that is located east of the Yampa Valley and Steamboat Springs. All right, so a little background on our samples. Samples were taken for about 10-minute integrals at Storm Peak Labs. Okay. And all the samples were taken using a two-stage mini impactor on aluminum substrates with a 50% cut size of greater than or equal to 0.1 micrometer and greater than or equal to 0.5 micrometers. So our mini impactor actually does have two impactor spots. It can produce two samples at once. And one of those samples will be on a 0.2 millimeter nozzle, and the other is on a 0.6 millimeter nozzle. Okay. Uh, for our cloud residual samples, a pumped counterflow virtual impactor was utilized, and this operated with a 50% size cut of greater than or equal to 25 micrometers. And our air masses were found to come back primarily from the west, which is over here. This is one of our air masses, for example, on this is at 4 p.m. UTC on the 21st of January of 2022 here. And so basically, we can see here that this came from this area here, Russia, Mongolia, kind of went through China, and then all the way up and over into Colorado, which is kind of where we are. I'll explain a little bit later whenever I get to more of like the data analysis and results. But um, yeah, basically, we see a little bit of an increase here. We have a lot of dust primarily coming through here, and we're kind of attributing that currently to like that and some other heavy metals that we find to this right here, the origin point here, and then it blowing across the ocean to Colorado. So here we go on to the next one. So one of our like other background things is going to be scanning electron microscopes with energy dispersive X-rays, which is one of the primary tools we use for our data gathering here. So all of our samples have about 100 to 200 particles analyzed, with the exclusion, I forgot to add, of some of the TEM grids. Our TEM grids had significantly less particles, and they were not handled as delicately, I guess, as they should have been. Uh, Considering we've never used TEM grids before, this was kind of a test. So they did have some damage, so the cells were damaged inside of a lot of them. So I could not find 100 particles really on them. But so a little bit more background here. So our electron beam will knock the K shell electrons out of orbit and cause them to emit X-rays, while the external electrons fill in the space in the shell. So basically, by doing that, we can measure like what angles it comes out at in order to determine what kind of particle it is, right? And yeah, the emitted X-ray is identified using energy and wavelength, which is just yeah, this E equals hc over lambda. Okay, and then over here on the right, I just kind of have a diagram a little bit of how this would work, right? So this is just our electron beam. It comes down, and then it shoots off these X-rays, cathode luminescence, backscattered electrons, Auger electrons, secondary electrons, all of this. And this is what we use to actually measure what kind of elements we are looking at. Okay, so I'll go on to the next part here. We have our cloud imaging probe. So basically how the cloud imaging probe works is the shadow images of the particles are collected after passing through a culminated laser beam. They are, let me make sure I'm still recording. Okay, awesome. They are then projected onto a linear array of 64 photodetectors. So the particle images are then reconstructed from the slices of data that these photodetectors basically have. And then these particles are then thrown into bin sizes, right? So multiple particles, anything below 15 microns gets thrown into the below 15 microns bin. Anything below 30 gets thrown into the minus 30 bin, and just increments of 15, basically. So a little bit of specifications on what we're using here for the CIP is our laser, which is 658 nanometers and 30 milliwatts. And if we look at a color for this, it'll just be in the red color range. Then our particle counts are distributed into bins, which I already mentioned, based off of the sizes observed. Over here, we just have a little diagram of how this cloud imaging probe is going to work. So yeah, basically these are the particles coming through in this direction, and then this laser is going to be able to, whenever it breaks, it's going to be able to tell pretty much how big the particle is based off of this diode array. So depending on how long the laser is broken, like the beam is broken by a particle, that's kind of how we determine the size there. Okay, we'll head on to the next one here. So now I'm going to go over a little bit of Raman spectroscopy. Raman utilizes the inelastic scattering of photons typically emitted from a laser. The photons are then emitted and excite the bonds between different chemical compounds. These rho vibrational angles are then measured and then used to identify the different bonding types to better notate what's happening, basically. So when the photons basically hit this particle, it'll excite the basically the bonds between them, and it'll cause them to rotate kind of like this. But then what we're doing is measuring at what angles, like how much they're actually rotating. And that's kind of how we are identifying what compounds there are. And this is typically done when to analyze the types of organic bonds that are present inside of particles. So yeah, this figure over here is basically just going over how a Raman spectroscopy works, really. So yeah, laser comes in here, goes through and hits the sample, but this also shoots it into a lens into the spectrometer. So we'll go on to the next one here. So for this one, we're doing size analysis and methodology. Okay, I'm going to go a little bit more in depth with what we're doing with this SEM-EDX data. So all images and size analysis are taken straight from our SEM-EDX. This is an example of a particle that I've taken over here from SPL 49.0.2. We then import these images into ImageJ, which is like very simple. It's just a program that you can download from a government website that's made specifically for microscopy. Okay. Sizes are then measured using a cross-section average and are graphed. Okay, I'll show you a little bit of that later. And then note most of these particles are only a few microns in size on average. To the left, or I guess my bad, to the right is an image of particle 45 from SPL, yeah, 49.0.2. Okay, so I took this image myself. It looks like I kind of cropped off the scale bar a little bit here while importing it into a PowerPoint, but I promise you'll use the whole scale bar whenever I'm actually doing data analysis on it. So we'll head on over here to the chemical composition method, which is a little bit different. So the atomic percentages are calculated with the electron dispersive X-ray function of our SEM-EDX. We then record those atomic percentages found and then manually select the specific 15 elements that we are interested in, which would be over here, these 15 elements. I think I need to put 14 probably. I would need to change that. But right now, whenever we're looking at our aluminum substrates, we're obviously not going to count aluminum into that because that would give us very skewed results for compositions, right? So the atomic percentages are then used in the equations provided in this image here, just so we can basically identify what it is. Okay, and then these calculations have also been taking the background readings of substrates. So we'll shoot the background 4 times in all 4 different quadrants, right? If it's a rectangle or a square, we shoot once in each quadrant where there are no particles at, and then we'll use that as a background reading. And then I'm subtracting that background reading from the data we're getting, right? So I'll get the raw data output from a particle, and then I'll subtract that background because we're a little bit worried about background leaks from that aluminum substrate. Okay. So yeah, note the chemical composition scheme has been used and published on previous research papers, which is just here. I added it in the references, so if you ever want to look it up and see why we do this, it'll be there. So we'll head on down to the next one for Raman spectroscopy. The Raman data was obtained at Texas A&M by my previous coworker, Dr. Elise Wilborn. Our spectra were collected by a Thermo Scientific DXR Raman spectrometer attached to an Olympus BX20 microscope and a charge-coupled camera or charge-coupled device, so CCD camera. These were then analyzed using a 532 nanometer laser with an intensity of 3.0 megawatts. They had 10 seconds per sample exposure and 10 exposures per spectrum. Okay. So aperture size was at 2 micrometers and it was a pinhole. And then the images were taken through a 100 times microscope with no photo bleaching applied to them. This intensity was specifically chosen by us to optimize the spectral intensity while limiting our fluorescence, and it also minimizes the damage done to the sample by doing the Raman on it. All right, so now I'll head to the cloud imaging probe methodology. Our CIP is used in order to capture the sizes of our incoming particles from outside. So this could be anything that ranges from like snowflakes to like very minuscule air particles, right? For the analysis of CIP data, I had to utilize our sample list at time intervals and match them to the same intervals from the CIP machine. I would then add those particle totals together for each size range. So for each bin size here, I don't actually have every bin size listed on this logs here. It's in the data, but obviously it didn't fit onto the range very well for the x-axis, so it's a little bit blown up here. But where was I? Then this resulted in us being able to see accurate size range and distributions of particles throughout our running times. To the right here is an example of our particle size obtained during experiment 38. I'll show you some more in a minute. And this actually allows us to see what the ambient weather conditions are. Basically, if we're in or outside of a cloud by looking at snowflakes that come through the CIP. So water droplets and stuff would typically make these bigger spikes in size, right? So if there's a lot of spikes in size over here, then obviously we are looking at like being in a cloud or precipitation is coming down our intake. All right, so now I'm going to go over to a few of the results. I have a lot of results. I probably could fit all of them on here, but it would probably take about 100 slides plus. So I just chose like 4 different samples-ish to look at. So here we have an example of our size analysis and composition comparisons. So this is for SPL 49, 0.2, and 0.6, which is just a millimeter size again for the nozzle. And this is an aluminum substrate that is in aerosol particles, basically. Okay, so as we can see in this, primarily we're looking at aluminum, silicon, calcium as our like primary group of particles. My bad. Yeah, composition. So we can also see here that, as we would expect, there is a larger density of particles at a smaller range here than that of over here at 0.6. So the 0.6 nozzle is letting in larger particles than the 0.2, which is basically establishing that our nozzle changes in size is actually working. So we'll go down here now to look at a aluminum substrate sample that is a residual sample, right? Which is just obtained differently, like I mentioned earlier. So what we can see here is, once again, it's predominantly this aluminum, silicon, calcium, right? And yeah, most of it is just going to be that. On this one, it also follows a trend. I guess I just put these graphs on backwards somehow, but this is 0.2 here and 0.6 here now. But yeah, once again, we see a higher concentration of smaller particles over here at the 0.2, which is always good to help us confirm what we are seeing. So as we can see here as well, this 0.2 on 50 here has quite a few more organic particles. It has CNO and CNOS particles more prevalent than that of SPL 0.6. And I forgot to mention that over here as well, we can see a lot of, or not a lot, but like a lot of CNO and CNOS particles as well, just on this 0.2. And then there's a few less, it looks like, over here on the 0.6, which is kind of contradictory to what we thought originally. As the Raman data that I'll show, or that I'll talk about in a little bit, will also say that we should have seen more basically organics on here. But the organics, I guess, could have been lost to like degradation over time or like temperature control and such. So we'll go on down here to our size analysis and composition. This is of our TEM grids. There's not very many particles, as you can tell, but this one's one of the aerosol ones. So this is put on a 0.6 millimeter nozzle, and basically this one is coming up as pretty evenly dispersed, maybe a little bit more of the aluminum, silicon, calcium on this than the sodium and magnesium. And then we'll just compare that to this TEM grid. Oh, I forgot to change it here, but this one's going to be a residual. Okay. But yeah. So for this one, once again, we can kind of see, I can't really get too much data out of it because there's not a lot of points, but once again, we're just seeing a lot of other here, which would be mostly like heavy metals. It'd be like iron, zinc, or like manganese, that kind of stuff. And yeah, so that's about what we're seeing from these. There's not much we can tell from such a small sample group. All right, so now I'll go on down to the Raman data for SPL and 49 and 50. Our Raman data analysis allowed us to identify specific samples which indicated increases in the amount of organics in those. So the ones that specifically were identified to us were like 49, 50. That, like, I think those two were the most specific ones. But so basically we would analyze those samples under SEM-EDX and compare them to the results to confirm that there were higher organics present. And we did find that there was an increase in CNO and CNOS particles in these samples compared to some of the other ones we've been looking at. And these were also pulling up quite a bit of phosphorus here. So we found that to be kind of unique as well. So now I'm going to go ahead and go down to the CIP data analysis here. So for our CIP data, we can obviously see, I was talking earlier about having just like these kind of upper range size particles. So what we can tell basically from this is this was probably in like inside of a cloud in a storm period, which actually I think confirms with what our person on site noticed and wrote down as like their observation of weather. And then from here we can also kind of see that it was probably storming, but it might have been like starting to calm down a little bit or something of that sort, because there's quite a less concentration here as compared to 49. Okay. We'll head on down here to, these ones are just the TEM grids. I just decided to do the same experiment numbers just to be a little consistent there. This one, once again, looks like it's probably within a storm just because of the size ranges here. And this one could be in a storm, but like it also is probable for it to just look like that, because there's obviously it could have been like ambient particles, and this could have been like caused by maybe like snowflakes or something going through the CIP. As there's like no filter or anything on the CIP, it just takes in like the raw air outside. So if it rains or snows, it just kind of goes into that, and then it takes the sizes of that. Okay, so go to one of my last slides here. So since I couldn't include all my samples that I've worked on, I actually did just go ahead and include, like, this is a list of all of the samples I worked on over for this project so far. I still have like 3 more to go, I think. But yeah, this just lists their sample types, substrate types. If we've done Raman data on them, this is where the weather conditions kind of came into play. That I don't know if I mentioned it earlier, but we used a specific site to find the weather conditions at the lab. So that gave us our temperatures and our average air pressures and our relative humidity. A little thing I noticed from this is in the winter, we see all these samples that are like 99% plus humidity, right? But then in the summer, we obviously see these last two here are summer samples, and we obviously see a lot less humidity in the summer from Colorado. Now, this also, I guess, could probably be affected. It was wildfire season when we went and took these, and it was very hazy from like smoke presence there. But I'm not sure if we could attribute that to the lower humidity or not. But yeah, that's about it for this. And then I'll just show you my references real quick. So yeah, these are just the references that I used, and I labeled them throughout the slideshow. And then let's see, I wanted to show you one or two other things. So previously you had talked about like how we had progressed. You wanted to see how we progressed from like the beginning of our research to like the end of our research. And I guess the end of my research is coming up like next semester. So I want to show you like around where I started and how it was going. So this is like basically my Excel files for like the first times I ever was working on these kind of samples, right? And this is from a different location. This is not from SPL, but this one should be from Alaska, I believe. But we'll see. I used to have to calculate all of this stuff manually by going through here and looking through each particle's individual data, adding it all, and basically just having to do a lot of manual labor for this kind of stuff. And yeah, this is like obviously I still have to calculate the size manually, but it used to take me a lot longer to do this kind of stuff and make like the combined categories, and I'd have to color code everything and like basically count it after I color coded all the size ranges. But now I want to show you what I'm working on now after about a year and a half or so of doing this kind of job, and I'll show you what I have now. So this is now my spreadsheet type that I use. It looks really complicated. This is actually for my Alaska samples again, but this is from like a year later, basically. I could show you the SPL stuff, but this is the most recent ones that I've been working on. So right now, basically what this does is it can take in the background. I have this is kind of what it looks like. Let me move this thing over here. But so you'll input like the raw data output. I'll show you one of these. Like this comes out of our SCMEDX auto detected, right? With this spectra data. So this is what it looks like after we select all of the elements we want to specifically look at, right? So I'll have it pasted into here. And this works the same way on the background, actually. But it'll basically import the background data into here, take the average of that background data, and then it'll do this background correction from that background data. And then this will be all of the raw particle data. This just pulls from each one of these individuals like sheets, right? And then it just throws it in here, and then it'll average it out, and it'll put it here, right? So we'll have our average of each type of element for our 100 particles, right? So then what it does here is this after correction tab, we will go ahead and it subtracts this background correction from this average before correction to create this average after correction, okay? And then from here, we take the standard deviation of that. We can also find the standard error, which is pretty nice. And then, yeah, from there, that's how I get most of my particle data for this summary of like averages here. So I will go on to a different part here. So this is all automated, by the way, so that's pretty cool. Then I have it go through here. So this will individually take each one of these and it runs it through basically like a set of equations, right, that are specified in true false statement form of the diagram I showed you earlier in the PowerPoint. So it actually follows what this is saying here, and it translates it into if statements here for me, and it outputs true and falses. So then from those true and falses, I can use an if statement here to basically classify what kind of particle classification we want to have, which is pretty cool as well. I'm very proud of this so far. And actually today, on these samples, they're from Alaska by the ocean, like pretty much at the most northern point in Alaska. So we needed to look at sodium to chloride ratios, look for chlorine depletion, right? So earlier today, I went through and I programmed how to find the average here of all of this. I had to do it manually because I basically have it. If it's we're setting thresholds here where if the sodium to chloride ratio is above 10, it's considered an artifact right now. But I can easily change that depending on what we eventually want to set as our permanent artifact number there or threshold value. So yeah, this will basically calculate the average here of this method one, which we can see here. It's just a different equation basically. But this will pull from here. So this gets rid of all of our artifacts down here at the thresholds for NaCl. So let me see if I can even find one here. This one might not have a threshold that's needed. Let's see. Let me scroll up a little bit. Sorry, I don't mean to take so long, but I just wanted to show you this because it's really cool in my opinion. Here's one for example. So the sample 31 here, you see how we have a like it's literally just sodium divided by chlorine, right? And it's above 10, right, for this ratio. So I set it all equal to 0 here. And then inside these equations, I tell it to omit that because obviously we're taking that as an artifact of information. And then from here, it's also calculating the standard deviation and then the standard error. And these are for 3 different methods of calculating the chlorine to sodium ratio or sodium to chloride ratio. So yeah, that's what I did today at work, and that's pretty cool. And obviously this is all automated as well. It counts it down here, it counts all these values, and it'll put it up here. And this is where we can see our total number of particles that I did analysis on. And yeah, that's about how that one goes. It also takes in the size. If I go over here to the combined categories, the graphs I showed you earlier, actually, this is how I generate them now. It just kind of it automatically does it. It takes this from the other part of like from this chemical composition tab. And then this is obviously just taken from me doing the sizes here where it's just the X value and Y value, add them together, average them. And yeah, that's how I get my size distributions. And yeah, that's about how that goes. I hope I'm not boring you too much with my explanations of that. But we'll also go here to I was going to show you a little bit of difference in like how I've gotten better at SEMEDX video like picturing. So this was one of the first samples I worked on for picturing, which was a PM1014, right? Which was the Excel sheet I showed you first, which was kind of outdated now compared to what I normally do. But this is one of the images from there. And then this is one of the images that I took really recently. And from what I can tell, it looks to be like I'm getting a lot better at it. At least for like focusing it and then getting the colors right, so you can actually see like physical like properties of the particle. Like you can tell there's an indentation here, or like that there's also like a fall off here. But yeah, I was just gonna show you that and update you about that and let you see my progress on how I've gotten better at SEMEDX. Data analysis, everything pretty much. But yeah, hope that wasn't too long of a presentation, and I hope that you enjoy it. I'm going to thank you for watching, and I'll catch you next time. Have a good night.